Yes, we can see your screen.
Yes.
Yep. Okay, so it's my pleasure to introduce today's speaker. It will be Giuseppe Negro from University of Birmingham. And Giuseppe will tell us about the intermittent symmetry breaking for the maximizers to the Egmont-Hermander estimate on the sphere.
Yes.
So Giuseppe, please.
Yes. Thank you, Alexander. Yeah. Thank you guys for inviting me to this webinar. I gave a talk last year, roughly this time of the year in July, so it's getting a nice.
Good to have you back.
It's a nice habit. Also, thank you a lot to Alex, who it was scheduled to talk today, but I had to switch for a last minute commitment that arose. So thank you for changing with me. And one word of apologizing. This work is not yet on the archive. It's brand new. I was going to put it on the archive before next week. Then the talk was moved today, so it's not yet, but it will be soon. I'm sure it will be soon. It's almost ready. And okay, and it's a joint work with Diogo Oliveira Silva. Diogo is a researcher at Birmingham, and it's also the founder of my postdoc there. And okay, and that's it. Without any more ado, let's move to the mathematics. Okay, so I'm going to talk about Egmont-Hermander estimate, and which is an estimate in at the crossroad of harmonic analysis and partial differential equations. Actually, Egmont and Hermander are big names of 21st century differential equations. But this subject is interesting because it allows two interpretations, as it's often the case with the Fourier transform. So let me start by giving just one slide of introduction to the result of Egmont-Hermander. This is all very classic. What is written. I'm going to talk about the Fourier transform, which, as you may know, is this operator. It's integral of, here I am doing the Fourier transform of a function, f function. And as you know, it's the integral of a function against the character, provided the function is integrable and all of it. You can do the same for a measure, and it's exactly the same object. You integrate a character against the measure. This is what in probability is called a characteristic function, but it's not important. Of course, here I am assuming implicitly some regularity on the measure. It should be Borel, it should be finite mass. And that's all I'm assuming. I didn't write it to avoid overcharging the page with notation. Now, for functions, which is this definition, one of the seminal results of the Fourier transform is the identity of Plancherel, also known as identity of Parseval, which essentially says that the L2 norm of a function, the integral of the square, equals, okay, up to normalization constants. In this talk, the normalization will always be this one. So the L2 norm of the function equals the L2 norm of the Fourier transform. And now the question arises, what can you say about this identity in the case of measures? It's not just a curiosity, it's important because very often this is the representation formula for a partial differential equation, such as the Helmholtz equation. I will talk about this later. So it's important to estimate the norm, the L2 norm of an object such as this one. But this cannot work verbatim. And I proposed here an example, which is also the right, in my opinion, the right entry point to the estimate of Agmon-Norman. If you consider this measure here, the uniform measure on the sphere, the round sphere, and uniform measure is, I call it uniform measure, sometimes it's the surface measure, as you wish. So there is a computation, which is this one, and this is a classical computation of analysis. Here R is the radial coordinate on R3. And the Fourier transform of this surface measure is the sinc function, this function. This is a classical computation which you can find in many books in analysis. I like it as it's done in the book of Jerry Folland, Real Analysis, for example. But it's everywhere. You can find it in many places. So if you now try to take the L2 norm of this function, of this sinc function, which is what I'm doing here, which is what I'm doing here. You try to do the L2 norm of this, you integrate in polar coordinates, so the x becomes r square dr, and then the data and the other polar coordinates on the sphere. The r square cancels with the r square coming from here, and you end up with this integral. It's a simple computation. And this is infinite. You are integrating a function that does not decay at infinity. But you can see that it's really borderline, because it barely fails to be integral. Well, not barely, it fails to be integral by a factor which we can put in, which is what I'm doing here. So if instead of integrating on the full space, I integrate on a ball of radius r, and I divide by the radius of that ball, so I get essentially the same thing as above, but now the integral is from 0 to r, which is the radius of the ball, and then is divided by the length of the integral. And since this is a periodic function, this is an easy exercise in analysis, this converges to 1/2. Okay, so in particular, this you can replace it by 1/2, and actually this you have a remainder of order 1/9. Not that it's important, but just what I want to say here is that this integral now, if we do this normalization, we integrate on a ball and we divide by the radius of the ball, we get something that is uniformly bounded, and it also has a limit. Whereas before we integrated on full space and we didn't get anything meaningful. Okay, so this is the entry point to the estimate of Agmon-Norman, and I want to focus the attention on this constant 1/pi. Let's remember this 1/pi, which arises here from this 2pi over to the 2pi cubed, and there is a 4pi here, there is a square, and in the end you end up with this 1/pi. 1/pi is an important constant in this talk because now it's time to review the result of Agmon-Norman. So Shmuel Agmon and Lars Ormander, 1976. This is a paper on asymptotic properties of solution to elliptic PDEs in general. And from that paper, I extract this result here. considering the sphere, the paper is not, this paper treats general compact manifolds. But I'm studying the sphere because for reasons which will be immediately obvious. So considering the sphere and the measure on the sphere, sigma will always be the surface measure on the sphere. And there is no need to stick with the 3D case. I'm considering the general dimension case, dimension at least 2. So we have this inequality. You can see that this operator here, this norm here, is the one that we considered before. Before we didn't have a function f multiplying the measure on the sphere. We had f equals to 1. It turns out that what we did before is the correct normalization for arbitrary functions on L2. So if we take a function, and the right way to think of this function is as a density. It's a density on the sphere, continuous, well, not continuous, L2, square integrable density on the sphere. You put it on the sphere, and the Fourier transform is bounded in this way. This is the result which I'm going to talk about today. And also, what's really important for them, this operation has a limit. If you take a limit, the limit of this, exactly as before, you have this constant 1/pi appearing, and then the L2 norm of the density. Okay, the proof is not hard, by the way, but the computation we did before was a nice special case that gives the feeling of what's going on. Okay, so in this paper, these people don't care about best constants. They care about full generality, so they don't give any information on this constant here. And this is where Diogo and myself come in, because on the other hand, we care mostly about best constants. And so we wondered, what is the best constant for this estimate? So in an estimate like this, the best constant is the smallest possible. And so I write best constant to say the minimal possible value of the constant in this estimate. And our result is that we can compute it explicitly, and it's given in terms of the Bessel functions. There is an expression with two cases. So depending on the sign of this product of Bessel functions, the best constant obeys this law or this law. So, and in this formula, I am using this notation of no is this coefficient. This is typical in the theory of Bessel function. It's a usual notation. And also, of course, the Bessel function of the first kind. I'm not going to give the definition. It's luckily, even though I don't really like this first kind, because it's not very illustrative, but it's a notation that is quite common. Okay, so now let me show a picture. So this is the result about the constant. The best constant in that inequality is given by this gray line. You can see that it's not smooth because there are at the zeros. So remember, there is a function which is the product of two. Its sign tells you which of the two branches you have to choose, this one or this one. And so effectively, after sign changes of that product of two Bessels, you have here a point of non-smoothness of the constant. So already this is a nice, I think it's nice because it's it's not immediately clear why this function should be piecewise smooth. However, what is really interesting, in my opinion, about this result is the next part, which is this one. So here I've written a recall. We are concerned with this constant, which is not really a constant, since it depends on the dimension and on the radius r, and which is the maximum over all functions in L2 and here of this norm here divided by the L2 norm of the density in L2. This is what we are studying. And of course, this is the best constant of the inequality which we saw previously. So the inequality of Agmon and Neumander tells us that this ratio is uniformly bounded in F. And now we want to start to compute the exact maximum. And the maximizers. These are the maximizers I was referring to in the title of the talk. The maximizers to this maximization problem, which is, by the way, the reason why I think this might be interesting for this webinar, since, as you see, it's a problem of maximization, not of discrete points on the discrete clouds of points on the sphere, but of continuous densities on the sphere. It's a maximization on the sphere. And the maximizers are have an interesting law, because they are, you can see, generically they obey these two cases. Generically, they are either constants. C is just a constant, any constant, or polynomials of degree 1, but homogeneous polynomials of degree 1. So no functions of this form, no constants. This is the generical. And then at the zeros of this function, which is a product of two, so at the zeros of the first, they are a linear combination of the first two cases. So constant plus a polynomial of degree 1 on the sphere. Oh, by the way, here I am putting these gray boxes sometimes. This is the notation I'm using. So I'm working on the sphere, dimension d-1. So a point is given by the coordinate. Of course, here it's implicit that the sum of the squares is 1. But I'm treating the coordinates as Cartesian coordinates. And yes, and this is especially important in the last case, which is the biggest one, the one with the biggest degeneracy. At the zeros of this Bessel function, the maximizers are given by a general harmonic polynomial of degree at most 2. So the situation on picture is the following. Yeah, this is the same picture as before, but I will note down only the dimension of the space of maximizers. You may have noticed that the maximizers are always a vector space. So at any r, you have a vector space of maximizers. When r is in this interval, which is, remember, there is this function here, the dashed, green dashed one, which according to its sign determines which of the branches of the constant to choose. So, and when the sign is positive, so we choose this branch, and the maximizers are constant, so dimension is 1. Then there is the first zero of this function, and the maximizer jump. Here, dimension is d plus 1. Maximizers are constants plus homogeneous polynomials of degree 1. Then again, a generic case, here the function is negative, and the dimension of the space of maximizer is d, because it's homogeneous polynomial, degree 1. And then there is, all of a sudden here, the maximal jump. This is the dimension of the space, I called it H2, of harmonic polynomials of degree at most 2. You can compute it, it's not hard. You just subtract 1 to the space, to the dimension of the space of all polynomials in d dimensions of degree. And then again 1, and then d plus 1, and so on and so forth. And this is what I consider to be the most interesting feature of this result. The fact that maximizers change and the dimension changes rather dramatically, and also the symmetry changes, because we have here spaces of constant maximizers, here and here and here. And then we have spaces of, when these d maximizers are polynomials of degree 1, so less symmetric maximizers. And here we have at the points maximizers which are even less symmetric, especially at these points here, where we have a rather big, surprisingly for me, big amount of maximizers. This is more or less what I tried to explain in this slide here. Why should we care? Why do I find this interesting? And now I can play with my cards fully on the table. This Agmonor-Mander thing is an important result in PDEs, but that's not the reason why I got interested in it. Instead, the reason is that these people, possibly without knowing, because they came in at a time in which harmonic analysis was creating the restriction problem, which is one of the main problems in harmonic analysis today, and which is, in a nutshell, it's the problem of establishing bounds of this form. This is the restriction problem on the sphere, of course. And here I put L2. People study this in much greater generality, but for the sake of definiteness, I put here L2. And so here you can see that if you choose this norm to be the one I introduced in the very beginning with this 1/r thing, this is an estimate that fits in this framework, even though it's very simple. More people are interested in cases in which this space is LP, and for even exponent, in some cases you can say which are the maximizers. You can compute the best constant, you can compute the maximizers, but the maximizers in all these cases turn out to be constants. And constants are fully symmetric functions. So here you have an inequality which is rotation invariant, of course. Here you take a space that is rotation invariant, typically. With it, our space is rotation invariant. So you might expect the maximizer to be rotation invariant as well. This was always the case for these estimates there, but it's not the case for us, because you have some, it's intermittent. So for some values of the radius, it is. But then there are jumps, there are discontinuities in this maximizer. This is the phenomenon that we call symmetry break. A reason why we think it's. Okay, so let me spend a few words about the proof of this result, and I will compute the best constant. And let's see how we manage to compute this constant, which is the constant. We call it the maximum of this ratio. This is a notation I introduced, of course. The spherical harmonics. Spherical harmonics are, you can define them in a variety of ways. I am using here these Cartesian coordinates. So it's convenient to define them as homogeneous harmonic polynomials of degree k. So always this letter will denote a homogeneous harmonic polynomial of degree k. And the advantage of doing so for us is that if you decompose the arbitrary function here into a sum of spherical harmonics of different degree, then the orthogonal also decomposes. This is a basic orthogonality property of the spherical harmonics. And what's more, since this object here is an L2 object, this also decomposes. And this is the reason why we can really say everything about this problem. And because it's easier, because it's orthogonal, it's an orthogonal problem. You have orthogonality here, and then both terms of your ratio decompose in a sum of squares with some coefficients, and then I will say more about this coefficient in its coefficients in the next slide. And so now the computation of the best constant is routine. This is a very easy fact. You want to maximize an expression such as this one under this ratio. Obviously, the maximum is going to be the maximum of these coefficients. So, provided it exists. It exists. We will prove in a moment that it exists. Otherwise, I should have written a soup here, but I think it's clear what I mean with it. So this orthogonality allows me to reduce the problem of best constant to a maximization problem of a sequence of coefficients. And that's not all. Moreover, these coefficients, I haven't written how I computed them, but it's a classical computation using polar coordinates and the Fourier Transform. You can imagine that Bessel functions will come out. Bessel function appear, the Bessel functions appear every time you use polar or cylinder coordinates, and you separate variables in some equation which contains the Laplacian. And here we have this Fourier transform on the sphere. It's something that's highly symmetric. So Bessel functions are bound to appear. And indeed they do. These are the coefficients. And so now you can see that we can do something. We have to compute the maximum of these coefficients. And these coefficients turn out to be, I hate dropping down a formula like this, but you can compute them explicitly. And this is even called the Lommel integral. We worked a bit on this, and then we discovered that everybody knew about that. If you search Lommel integral on Google, you will find a plethora of information. This is one of the many well-known identities about Bessel function. I'm not going to prove this. It's classical, but I'm going to prove something similar but easier in the next slide, just to give a feel for this kind of computation. What's important is that here you have this weight. This is the natural weight for Bessel functions. Okay. And so now, and this is the computation that I want to show. Let's spend a little bit of time on this slide. So remember, we wanted to maximize, to find the maximum of this. So we want to find the maximum for k in n of this. But now, with this computation that I'm going to present you, I claim that it's actually enough to compute the maximum of the first two objects. And the reason is that there is here an identity which I'm going to derive. So consider the generic lambda k coefficient and take the difference with the lambda k plus 2. Also, remember the coefficient was the integral of the relevant Bessel function squared with this weight. And there was a factor 1 over r. The factor was here. I put it here so it's out of the way. So we are computing this kind of integrals. This is the difference of squares. So you can write it as, this is elementary, as a sum times a difference. And now, Bessel functions, there is a fundamental recurrence of, perhaps is the most fundamental identity of Bessel function, the recurrence relation. They say that if you take the sum of two Bessels, such as these two, in which you have the difference is 2, the indices differ by 2, such as here, nu plus k, nu plus, this is k plus 2, sorry, there is a mistake. That's not correct. This should be, yeah, it was wrong. It's this k plus 2 propagates here and it propagates here. K plus 2, k plus 2. Now it's okay. Sorry about the type. So you have a difference of Bessel function. Yeah, I'm sorry, a sum of Bessel function that differ by 2 in the argument. And the sum is up to constants, which I'm not considering now, is the Bessel function in the middle. So k plus 1. You have here plus k, k plus 2. The Bessel function in the middle is the sum. And the derivative of the Bessel function in the middle is the difference. And so you see that this integral is explicit because this is the derivative of the square of the Bessel. Forgetting about constants and all of that. And this being a square is not negative. So this means that lambda k is bigger than lambda k plus 2. And so we have two chains of inequalities. The 0th lambda controls the second, which controls the fourth, and the first controls the third, which controls the fifth, and so on and so forth. So it's enough. We want the maximum. It's enough to consider the 0th and the first in order to determine the maximum. And this is where these two branches come from. Because then, and by the way, this computation is rather simple, but more or less it's always like also the other one, the one from the previous slide, this one. The machinery is the same. Recurrence relations, ODEs, it's very classical mathematics. So here, this is the formula. By the way, I didn't say this, but of course, this is the formula that appeared in the first slide, the formula for the best cost. And now we can finish the proof, we proved that this C sub d is the best constant, the object we want to compute. It's the maximum of two coefficients. And then there is a computation, but this is also easy. The difference between these two, using their explicit expression, is exactly that function which was in dashed green in the picture, which controls, which is with its sign, this one here, which branch of the lambda to choose. And this is why the constant is like that, is piecewise as well. And then with a little bit more of attention to the detail, you can also determine the maximizers, which are going to be spherical harmonics of low degree. And that's all I wanted to say. Thank you.
Great. Thank you, Giuseppe, for the nice talk. Are there any questions, comments? So I have a little question, maybe just to start. So yeah, so I was just thinking about the multiplicity. So this guy here, this product J nu plus 1, right?
Yes.
The zero, the multiplicity of 0 is 1, right? So like this, right? So yeah, so but the degree. So somehow I was trying to understand the degree of the space of minimizers goes from 1.
From 1 to d plus 1. Yeah. No, I think it's unrelated to this multiplicity. This is a simple 0.
Right.
Because you see here, all zeros are simple, and but the space of maximizers jumps. It's not related to that.
So it's not just that. Okay.
Yeah. Yeah. No,
Yeah, but
it's an observation.
Yeah, but it's nice you get these test functions from so they are just harmonic polynomials of degree 0, 1, and 2. So that's kind of cool. Is there a way, can you just look at the equation and maybe see why they should be harmonic?
Harmonic, it's because they are spherical harmonics.
It's just that, never mind that. Yeah, okay.
It's a way of writing.
It's silly. Yeah, of course.
Yeah.
Silly question.
Yeah, no, but I don't see a way of looking at the inequality and saying the maximizer is a spherical harmonic of degree 2. I don't. Yeah. I think it's surprising, to be honest.
Yeah, it's quite interesting. Yeah, so we get these. So we like to think about cases where sigma is the extremizer. So you have uniform functions, uniform densities, I guess, or something, but also you get these non-uniform degree 2. Yeah,
uniform wins here, and then non-uniform wins here, and then there are exceptional cases in which it's crazy.
Right.
Yes, and then it goes. So this is the reason why I use the word intermittent, because I wanted to say periodic, but this is not exactly periodic.
Yeah, right. Yeah, it's. I think is that right? It's periodic in the limit or something like that. Approach it. Yeah.
In the limit.
Perfectly periodic.
Yeah.
Yeah, because this is. I mean, it's the zeros of Bessel functions determine this. And the Bessel functions are, for big argument, they are cosine, almost cosines.
Right.
So the zeros, later on, they will start to stabilize. I didn't write, this is the picture corresponding to dimension 2. Yeah. So in the, I mean, this is a small graph, but if you can see that it stabilizes here. So in the beginning, it's a bit crazy, and then in the end, this is it gets. And also, we recover the limit. This is another thing which I didn't say. In the paper of Agmon and Olmander, there is this constant 1/pi, which is important for the sphere. The constant, of course, depends on the manifold. If you take the sphere, you have 1/pi, and we recover it as the limit of this oscillating thing.
Okay, so
sorry,
yeah, go ahead.
So the picture is for dimension 2, and in dimension 2, the dimensions of the space of maximizers at the roots of these of this function, they will be the same, right? It will be dimension 3 everywhere, so they do not alternate, right? But you get different maximizers. Right? So the dimension is all this. Okay.
Yeah, you are right, because this.
And in between, it's either 1 or 2. Okay.
It is a 1 or 2. Yeah, so it's 1, 3, 2, 3, 1.
Okay, interesting. But so you have the same dimension, but different maximizers, right, at adjacent roots. Okay.
Yeah, I'm not. Maybe it turns out to be the same.
Oh.
Yeah, it's a good question. I don't. Can be that it's the same, because I mean the maximizers are. So this expression here, it reduces to x plus y, but if you should really write things down in terms of sines and cosines, and then probably there is some simplification. Yeah, this is a nice observation. I would take it. Yes. Yeah. Yeah, thank you. Good observation.
Cool. Any more questions?
I have a small questions, maybe stupid one. At the beginning of proof, you wrote expansion function f in terms of spherical harmonics, but should be there some coefficients?
Yeah, this is in the beginning I used to get.
Yeah, you just already like decompose f.
Yeah.
Should be here some coefficients, right?
But I mean, this is the Diogo likes this notation. I used to get the exact same confusion as you. So the spherical harmonics are not fixed. This actually, right, this depends on f. So so the coefficient is incorporated into yk. We haven't fixed a base of spherical harmonics in the beginning, and then you compute the coefficients. Now this is a spherical harmonic.
Okay, they're just dependent on f. That's why you can.
Right. Yeah, it's a way of writing. It's a bit more compact, but yeah, I used to be confused exactly like you, but it's very common in these papers. Damiano Foschi used it also, so I adopted it.
Okay.
Yeah, I think the point is, once you decompose your CD of R, the sum of squares, it just doesn't matter what the coefficient is, right?
Exactly. Yeah. So you don't want to make a big fuss about it, because really what you are interested in is these coefficients and the Bessel function. Exactly.
Okay, so maybe one last question, if there are none from the audience. So you started talking about, you said the magic word manifold, and that really begs the question. So you probably were thinking about this on other manifolds.
Yeah, but for the moment I don't have any result on this, because of course here the sphere, if you consider the sphere, you have Bessel functions, spherical harmonics, all well studied. You have every possible formula that you will need is there, such as this one. But if you take another manifold, say even an ellipsoid, for example, you are going to have, how do they call them, ellipsoidal spherical harmonics and this kind of ellipsoidal harmonic. I mean, it's more complicated from this point of view. It's technically harder. But of course, it's a very good question if this is this behavior is specific of the sphere or if it's generic in some sense. I have no clue on how to answer, but it's a natural question.
Yeah, somehow if you write yk, and so you basically just needed an orthogonal basis, and the fact that you knew what Fourier transform. So basically, the fact that Bessel functions pop out of the computation, right? So so somehow, if you have orthogonal basis and you know behavior of the measure under Fourier transform, seems that maybe there's a chance you could work. Yeah, there's a chance you could work out the details.
Yeah. So said otherwise, if you change the measure, you lose Bessel function. You cannot rely on explicit Bessel functions, on explicit spherical harmonics, and then it's harder. I don't know. Okay.
Right. Okay, last call for questions on the record. Okay, if not, I guess we can stop the recording. So let's do that.